Okay, this is a paper from winter 2019, paper 51, and it's obviously not the alternative to practical, it's the planning paper. All right, there's a lot of stuff there. I'm not going to read through it all, but you've got to calculate the minimum masses of barium carbonate and copper oxide that are needed to react with 0.750 grams of yttrium oxide to give a yttrium barium copper ratio of 1:3. Okay, so we've been given yttrium oxide. Let me get a nice pen. We've been given yttrium oxide, which is that. Okay, so that's got two yttriums in. So to give me a 1:3 ratio, I need 4 barium barium carbonates, and I need 6 copper oxides. So that's the ratio I need to give me a yttrium, where is it now, barium copper ratio of 1:3. Obviously it's 2:4:6 here, but it's the same ratio, isn't it? All right, so there you go. That's all I've got to do. It's not so hard once you realize what you've got to do. Okay, so now let me get a different color pen, a blue pen. What's the number of moles I have of yttrium oxide? Number of moles of yttrium oxide is 0.75 grams divided by the relative molecular mass of yttrium oxide, which is 225.8. 225.8. You can work that out yourself. I'm not going to do that for you. All right, so now where are we? Where's my calculator? Right in front of me. Okay, so it is 0.75 divided by 225.8. And that gives me 3.2. Actually, the pen's a bit dark, isn't it? Sorry, a bit light. So 3.32 times 10 to the minus 3 moles. That's the number of moles of yttrium oxide. All right. Now I'll times this number by 4 to give me the number of moles needed of barium carbonates. So it's this number, 3.32 times 10 to the minus 3 times 4. And that equals times 4 equals 0.013. Sorry, messed that up. 0.0133. That's the moles I need of barium carbonate. And the number of moles I need of copper oxide is this number again, because these are the ratios. Times 10 to the minus 3 times 6. So 3.32 times 10 to the minus 3 times 6 gives me, very close to 0.0200 moles. Okay, of copper oxide. Now, timesing the number of moles by the relative molecular masses should give me the masses I need. Barium carbonate is 197.3. And copper oxide is 79.5. So just calculating those out. Again, you've got to work out these masses yourselves, okay? So let's see if I get this right. 0.133 times 197.3 gives me 2.62 grams of this. Okay, and the mass of the 0.02 times 79.5, it gives me 1.59. Okay, so that's that bit done. Let me stop the video and have a look at the next bit for you. Okay, the next part is this. I'm only doing the calculations, by the way. If there's problems with the other bits, give me an email and I'll do those. All right, so when starch indicator is added to step 4, the mixture turns blue-black due to the presence of iodine. The end point of the titration with sodium thiosulfate is a colourless solution. The number of moles of S2O3 aqueous needed for complete reaction can be calculated from the mean titer value, hence the number of moles of iodine can be determined. State the expression for the number of moles of copper 3 in the sample of that. Use A to represent the number of moles of iodine in step 4. So let me use a nice bright colour here. Yeah, this orange is good. If iodine is A here, it must be A here. If iodine is A here, the Br3 minus must be A. If this is A, this must be 2A, because I'm using the coefficients. So the answer there is very simply, number of moles in terms of A is going to be 2A. All right, next, calculate the mass of hydrated sodium citrate that would be required for the preparation of 250 cc's of a solution of 1 mole of citric acid. So obviously it's a quarter. All right, if I make 1 decimeter cubed, I need 1 mole. But I'm only making a quarter of a mole, sorry, quarter of a decimeter cubed. So it's 0.25 times the relative molecular mass of sodium citrate. Let me get rid of that, which is apparently 294. So 0.25 times 294, which is 73.5 grams. Okay, fair enough. Okay, next, whoops, move this up. Student places the mass of the sodium citrate calculated and seen into a beaker. Describe how the student can prepare exactly 250 cc's of the solution from the sample in the beaker. Give the name and capacity in cc's of anything you're using. Okay, so first of all, let's do it graphically. You should have a beaker. All right, the beaker doesn't have to be very big. Let's say, just for argument's sake, we're going to use a 100 cc beaker. All right, you put the sodium citrate in the bottom and add water. This is water. Okay, not only water, it must be distilled water. All right, and you stir. Okay, so I'm going to say add the sodium citrate to 100 centimeter cubed water beaker. Add distilled water. Oop. Distilled water. And stir to dissolve. That would be my first point. Now I would transfer to a 250 cc volumetric flask. Okay. And then I would, once I've transferred it, then I would wash out the 100 ml beaker, 100 cc's beaker, and transfer the washings to the volumetric flask. Okay, so I've put everything is in the volumetric flask, and now point 3, I would make up. Make up to the mark with distilled water. The mark, when we say this, we say make to the mark. In the volumetric flask, that means the mark of the volumetric flask. So there's the volumetric flask, and there's a mark there, and we say make up to the mark. All right, that's how you always make up a standard solution. You've got to mention distilled water. If you don't mention distilled water, you'll definitely lose a mark. All right. Last of all, let's have a look at this question. 1 second. Okay, so this is the last question. I didn't have the problem with the student's titration method and suggest how it could be improved. Obviously, this is a very vague question, but you can see that these are not good enough, are they? They're not close enough. Now, what could we say? They're not consistent. Okay, the titers aren't consistent. Titers are not consistent. All right, to be consistent, they've got to be within 0.10 centimeters cubed of each other. Now, a word Cambridge like is concordant, and that's another word for sort of close together, consistent. Okay, so you can use concordant if you want. All right, what would you do? Well, you've got to repeat until consistent titers are achieved. See, all you can do. You've got to do that. Okay. You repeat until the consistent titers are achieved, and that's when you get 2 or more results within 0.10 centimeters cubed of each other. Okay, horrible question. I wouldn't have thought of that because I would have thought method. Well, the guy's doing something wrong with the method. They should have replaced this word with results, and then it would have been a fair question. but it's a stupid question as it stands. All right, thank you. I'll let me post this.